Hello, and welcome to this clip where I will talk about the concepts of the total sum of squares for regression, and residual sum of squares, and of course, the relationship between them. Let us assume that we have an interest in two variables, an explanatory variable, x, and a response variable, y. Hence, given the value of the explanatory variable x, we want to make a guess about the value of the response variable y. We try to fit a statistical model that explains the variation in the response variable y by the explanatory variable x. To do so, we collect data. And in the plot, you see the data points, here 6 of them. One model that could reasonably fit our data is the linear regression model. Next, there is another line we could fit in this plot, which is the horizontal line for y bar, which represents the mean of the observations on the response variable, here shown in light blue. The total amount of observed variance in our response variable can be visualized by these vertical distances from each observation yi to the horizontal line at y bar, here given in red. If we want to quantify the total amount of observed variance, we could just sum these differences between yi and y bar. However, some of these differences are negative, as y bar could be both smaller and larger than yi. So big positive and negative differences may cancel each other out, which is not a good idea. When we take square differences to get rid of any negative signs, it will work out much better. Hence, we sum the squared differences. The outcome is the total amount of variance in our response variable around the mean, also known as total sum of squares. In a formula, it looks like this. Total sums of squares equals the sums of all square differences between observations yi and their mean y bar. This is the total sum of squares that we will try to partially explain by introducing the variable x into the game. When we fit the regression model, which is this line, we look for the line that matches our data at best. Best in a least square sense. Let's assume the best fitted line is the line in blue here. Corresponding to each value of x, there's a prediction on the blue line. These predictions are indicated here with blue dots. To obtain this least square estimated blue line, we want that differences between the observations yi and predictions yi hat from the blue line are as small as possible. These differences are indicated by the green curly brackets. Since negative and positive differences may again cancel out, we take square differences. The sums of square differences between observations and predictions is what we call the sum of squared errors, abbreviated with SSE. And it is the quantification of the error of the model, that is what variable x is not capable to explain from the variation of y. In a formula, this error, sum of squares of errors, equals the sum over all observations yi minus y hat squared. And you can see it here on the slide. We hope that the predictions from our estimated regression model, the blue dots, are in closer agreement with the observations than y bar, the orange dots. Note that y bar can also be seen as a rather crude prediction from a model with just one constant term only. For our regression model to be meaningful, it will have to outperform at least the crude prediction given by our y bar, that was the average of our sample. The improvement in prediction by the regression model can easily be visualized. It is the distance between predictions y hat and mean y bar, as shown here with the brown curly brackets. To quantify this improvement in one single number, again we sum over the squared differences, hence the formula. The sum of squares for regression, abbreviated SSR, equals the sum over all square differences between y hat and y bar. This quantity is the part of the total sum of squares that can be explained by the variable x. And there's a nice relation between these three sum of squares. The total sum of squares is equal to the sum between the sum of squares for regression and the error sum of squares. And you can see the formula here on the slide, of course supported by a very nice animation. By comparing the regression sum of squares with the total sum of squares, you can see how well your model is performing. Ideally, your error sum of squares is close to 0, and your sum of squares due to the regression is close to the total sum of squares, but obviously never larger. The ratio between these two equals r squared, the proportion of explained variance. This was quite a short clip, but by the way, do you know what is the sum of squares of the first 7 prime numbers? 666. Thank you for watching.